So, basic solidification mode in welding process can be represented in four different ways. One is that planar, that means the solidification front move in the form as a plane. Next, another mode of the solidification front that can create maybe by breaking the planar interface, and it can create the kind of cellular structure. Okay. And then during the solidification also, that there may be the possibility of formation of the another type of solidification mode, that is called column or dendritic structure. That means, the growth happens in such a way that it makes a big column and the primary and secondary dendritic arms attached with that column. So, this kind of structure also it is obvious from the figure that this structure actually represents the columnar dendritic type structure, and that actually happens during the solidification from the within the liquid metal transform to the solid phase. So, during that transformation it creates this kind of that means columnar dendritic structure. Of course, the dendritic structure can be formed in the like a equiaxed kind of structure. That means, it is like if you see the from the figure that there is a 3 arm and the secondary dendritic arm are spacing accordingly. So, that it looks like the equal amount of spacing in all 3 directions. So, it is a kind of structure or mode is kind of equiaxed structure, microstructure, what you say almost equal size of the grains throughout the microstructure. So, these are the 4 different types of solidification mode generally observed in case of welding process. Now, in much details solidification in welding process, and it is very much specific to that the alloy materials, basically solidification of the not pure metal. So, maybe we can say that in case of alloy metal that constitutional supercooling is the one of the important phenomena that is attached with the solidification during the welding process. So, supercooling we have some idea that from when during the solidification, that when the liquid molten metal comes around the phase transformation temperature, that means from solid to liquid phase transformation temperature. So, during that transformation and there is a amount of the supercooling observed in the liquid metal. Of course, it pertains with some conditions, that means that before starting of the phase change, the amount, the nucleation mechanism involved in the welding process or maybe solidification process, that actually governed by the what is the amount of the supercooling temperature. That means, the supercooling temperature below the solid to liquid transition temperature. So, in case of pure metal, it can be well defined from the time versus temperature diagram, and this amount of supercooling depends on the, or maybe values are the different for the different types of the material. So, normally the amount of the supercooling is mainly promote that the homogeneous nucleation, or maybe in case of homogeneous nucleation for in solidification process is mainly driven by the amount of the supercooling, which is entirely different from the heterogeneous nucleation mechanism. But constitutional supercooling can be defined in such way that it actually occurs during solidification and due to the compositional solid changes, which finally result in the liquid metal below the freezing point temperature, and that exists ahead of the solid liquid interface. Actually, this constitutional supercooling mainly affects or better describes the what is the amount of the supercooling that depends on the compositional solid changes specifically for the alloy material, and that amount of the solidification constitutional supercooling during the solidification in case of graphically we can represent here that this region marked by red color that actually represents the region of the constitutional supercooling, or we can say the amount of the supercooling in case of alloy. But this amount of the supercooling generally exists during the solidification process of specifically the alloy metal, but the mathematical term or parameters that actually govern or may be linked with the constitutional supercooling is that is better described by the one is the diffusion coefficients of the solute in the liquid. That means, this dl that represents the diffusion coefficients. If you see the unit of the diffusion coefficient is the length square per unit time. So, mainly it is a diffusibility, it represents the diffusibility of the solute in the liquid metal. Another parameter that actually used to describe the solidification behavior specific for the alloy material, that is the growth rate. So, that is the unit is that length per time or length per unit time, that is representation of the growth rate, and then temperature gradient. So, temperature gradient is the theta by L, that means it is the temperature per unit length. So, these are the typical parameters that actually involve to represent the constitutional supercooling during the solidification process. Now, we try to explain this phenomena graphically. That first, if we look into this first figure, there is a transition of the solid to liquid phase. So, here the growth rate is R, that means growth rate more it is linked that what is the what way that the solid liquid interface is basically moving. So, that zone between the solid and liquid, there is a zone mainly that is called the Mossi zone. So, in this zone the liquid and the solid phase coexists, but this depends on the or in the amount of the supercooling exists within the during the solidification of a specific alloy. Now, if we see the temperature versus concentration graph, here you can see the solidus line is there and then liquidus line and initial composition having the C0. So, this material is subjected to some amount of the supercooling. So, that constitutional supercooling is simply marked by the red color, and that means the temperature difference in this case is delta T. So, that delta T on the temperature axis, it is represented that between the TL and TS, that is the amount of the temperature decrement with respect to the initial composition. And if we see even with respect to on the liquidus line, the composition or concentration of the alloy material, here you can see that C0 by K, that is we represent that C that K equal to ratio of the CS and C0. So, from here we can this here composition is represented by C0 by K. Now, this amount of the constitutional supercooling, if we project in the right hand side figure, here if we see temperature versus distance from solid liquid interface. So, up to what extent from the interface it can go, that is represented simply just projecting this constitutional supercooling on the time versus concentration graph to the time versus distance graph. Here we can see that this is the on the this first slope is the actual slope. The actual slope is the temperature gradient represented by the mathematically represented by term Z, temperature gradient. And then if we look into the other slope, the slope of the tangent at this point, here we can see the slope of the tangent can be represented by what is the slope means, the change of the temperature, that means temperature difference with respect to some distance here, but here the distance can be counted maybe in terms of the boundary layer here, that is the diffusivity or DL, diffusion coefficient divided by the growth rate. If you see the dimensionally also, so this term delta T and DL by R, that also represents the slope of the tangent. So, in this case it is very obvious that definitely the actual slope from the figure also it is very clear, the actual slope g is less than equal to the slope of the tangent. That point of view we have estimated that during the supercooling what is the temperature difference and what is the amount of the distance travelled by the solid liquid interface in terms of the diffusivity and growth rate. So, here if you geometrically or graphically we can see this slope is basically less than that of the estimated slope here. So, to have the constitutional supercooling, so graphically we can say that this condition G by R less than delta T by dl, this condition is satisfying. So, that actually that is the mathematical conditions during the solidification. So, probably having in this case the constitutional supercooling. So, now we will further look into other condition, or maybe we try to explain physically that what is the mathematical condition for the constitutional supercooling and how it can be linked with the solidification behavior during the welding process. So, first comments is that of course, the shaded area that represents the constitutional supercooling, therefore, that region is consists of actually liquid alone is unstable. So, in that zone basically solid and liquid coexists. Now, to estimate that slope also we assume that the thickness of the boundary layer during the movement of the solid liquid interface at the steady state condition is better described by the dl by r. dl is the diffusivity divided by the growth rate, and that dimensionally it represents the length, dimensionally it represents in terms of length actually dl by r. Now, to avoid constitutional supercooling, we can put the condition just reverse having the constitutional supercooling. So, having the constitutional supercooling, this was the condition G by R less than delta T by dl. What to avoid constitutional supercooling, it is just G by R should be greater than equal to delta T by dl. These are the to avoid the constitutional supercooling. So, this mathematical condition is sometimes helpful to quantitatively explain the solidification behavior, that what are the driving mechanism whether constitutional supercooling exists or not, based on that type of nucleation, whether it is homogeneous and heterogeneous nucleation, that is better explained by these mathematical conditions. Now, the constitutional supercooling can also be explained in can also be used to explain whether there is a need or breakdown of the solid liquid interface can be stable interface from the planar solid liquid interface. That means, planar solid liquid interface is stable if not having the constitutional supercooling, that means just opposite to the condition of the avoiding the constitutional supercooling. So, in that sense G by R greater than equal to delta T by L, that actually represents for the stability of the planar solid liquid interface. Now, in planar solid liquid interface it may break also, and due to the cellular or maybe in the dendritic, so that solid cell or dendritics actually can coexist with the intercellular spaces or interdendritic liquid. So, that breakdown of the planar solid liquid interface to other solidification mode, cellular type or dendritic type, that dendritic type, that can be explained mathematically here also in terms of this G, R, delta T and dl or these parameters. So, higher G and lower R, that actually leads to the planar solid liquid interface. That means, if we look into the condition also that G by R ratio is very high, that means there is a existence of the solidification mode in terms of the planar solid liquid interface. Other side, higher delta T, that means temperature difference is very high. So, that means degree of supercooling is very high, and of course, more amount of the diffusivity dl, that actually leads to the more difficulty for a planar solid liquid interface to be stable. So, that actually breaks down the stability of the solid liquid planar interface during the solidification process. So, here we can say mathematically that two things, if G by R less than delta T by dl, that means there is a existence of the constitutional supercooling, that means non-existence of the planar solid liquid interface in this case. Other way also, if G by R is greater than delta T by dl, that means there is a existence of the, or that is a favorable condition to put the solidification mode in terms of the planar solid liquid interface. Now, here we can look into the different type of the solidification mode and structure. So, it is also necessary to mention that although these two parameters G and R, so G and R, these two parameters, that means temperature gradient and growth rate, they actually mathematically define the mode of the solidification at the same time, and also define the rate of the cooling. That rate of the cooling is decides basically that whether it is fine structure or whether coarse structure exists during the produced during the solidification process, and solidification mode decides what is the type of the, whether it is planar, four types of the planar or cellular, dendritic, columnar dendritic or EQX dendritic kind of structure. Now, if we see that four different types of mode is better, from this figure we can see that there is a four type of solidification mode: planar mode, cellular, columnar dendrite, EQX dendritic structure. Now, here you can see that increasing the constitutional supercooling is transform the structure from planar. So, that means very low amount of the constitutional supercooling promote to the formation of the planar kind of the solid liquid interface. But if the constitutional supercooling is very high, maximum in this case, they actually promote the structure like EQX dendritic structure, it will try to produce. Now, graphically also you can see that here the vertical line, the solid liquid interface, and that side the equilibrium temperature reach, and this is the, this represents the actual slope in the curve. So, in the that curve, the time and the solid liquid the distance versus temperature, in that case the actual slope. So, here if you see that the temperature and actual slope, they are not interfering with respect to each other. That means, there is a minimum amount of the, or we can say there is no constitutional supercooling exist. So, that promote the planar kind of the solid liquid interface. The mode of the solidification is basically planar. Next, if the certain amount of the increment of the constitutional supercooling, then it cross the slope is less basically, and then there is a shaded zone that is marked by the black, the shaded zone, and that actually produce the cellular kind of the solidification mode. Cellular mode, in this case, that means there is a small amount of the constitutional supercooling exists. If you look into the third, that amount of the constitutional supercooling actually increasing, and that try to produce the columnar dendritic structure, and finally, the maximum amount of the supercooling that produce the EQX dendritic structure. So, depending upon the amount of the constitutional supercooling, the solidification mode basically changes, or solidification mode can be decided. Now, here also other comments that the dendrites and the liquid phase coexist is called basically the Musi zone. So, in that zone where the dendritic formation of the dendrite and the liquid, they actually coexist, that is the normally called the Musi zone, and that Musi zone is basically in between the temperature between the solidus and liquidus temperature. So, at very high degree of constitutional supercooling, it is very obvious that the Musi zone becomes very wide. So, that zone becomes very wide, or at the other way, if low degree of the constitutional supercooling, there is almost no Musi zone, or Musi zone not very wide, small. So, here from that with respect to the point of the view that with the degree of the constitutional supercooling we can predict at least the what are the type of the solidification mode, whether it is planar, cellular, columnar dendritic or equiaxed dendritic structure. Now, here we like to mention that the two parameters, the temperature gradient G and the growth rate R, affects the solidified microstructure. So, two different ways. So, by combining these two parameters, the temperature gradient and growth rate, here you can see the product of G into R, this actually known as the cooling rate. If we dimensionally check it, then that G is the temperature gradient, temperature by length, and R is the growth rate. So, length by time. So, in that respect the length by time is basically temperature by time, that actually represents the cooling rate. At the same time, the ratio G by R actually determines the solidification mode, that already we have discussed, that depending upon the G by R ratio we can define the mode of the solidification. So, this combining these two G R and G by R, if you try to represent the one axis, the x axis the growth rate R and temperature gradient is the y axis, it is the G. So, this combining these two we can find out that different solidification mode this way, that planar, cellular, columnar dendrite and equiaxed structure. So, high G by R value that actually promote the kind of the planar structure, or at the same time low G by R ratio that actually promote the equiaxed dendritic structure, dendritic solidification mode. But if you see that from the graph also, if now we try to incorporate the effect of the cooling rate also. So, here this line that represents the rate of the cooling, so G R, and so first line alpha 1 that represents the low cooling rate, and if you see the alpha 2, the second line, this is represents the cooling rate on this graph, that represents the high cooling rate. So, if cooling rate is very high, overall microstructure is very fine. If cooling rate is low, the overall microstructure is not the coarse structure. So, basically higher cooling rate we can expect the fine structure, and lower cooling rate we can expect the coarse structure. So, greater G R, G into R, that means G into R, that means greater cooling rate, that we can find out the very fine solidified cellular kind of dendritic structure. If we see from this figure also that most of the structure exists in this case, that either cellular or columnar dendriting, and planar and equiaxed is the more two extreme cases here, but in general cellular and columnar dendritic structure exist, and it becomes more finer structure if cooling rate is very high. That means, it is beyond that zone, the second line corresponds to alpha 2. So, basically alpha 1 equal to 1 G 1 R 1, or alpha 2 is basically another value of G into R. So, from this figure we can explain also quantitatively that the whether it is fine structure, coarse structure, at the same time what is the solidification mode, or the what is the solidified structure, whether it is very planar, columnar kind of structure, dendritic, equiaxed, and all this kind of information we can get by analysis of this kind of figure. Now, come after solidification mode, we will try to look into the discussion on the weld microstructure. So, grain structure actually affects the susceptibility of the solidification cracking. So, it is very much linked with that, and finally, grain structure also define the mechanical property. So, it is it is necessary to link that what is the final microstructure and probably what is the expected mechanical properties, or whether there is any solidification cracking may occurs or not. That kind of information can be get if we analyze the mechanism of the grain structure or maybe weld microstructure formation during the solidification process. So, one important aspect of the growth in the fusion zone of the welded structure, that is called epitaxial growth at the fusion boundary, and this epitaxial growth basically happens in case of the autogeneous fusion welding process. So, if we use some filler material that actually destroy the epitaxial growth mechanism, maybe in that case some other mechanism can be better to explain the phenomena of the grain growth. So, epitaxial growth, we can see that molten metal first is in contact with the solid with the base metal, then grain growth initiates on that boundary or at the solid liquid interface, and it proceeds towards the weld central line. From the figure also it is very seen that very obvious that welding direction is there, and the oil pool, from the oil pool liquid oil pool, and that interact with the base metal. So, from that interface it growth happens one particular direction. So, that this type of growth is basically called the epitaxial first nucleation and then growth. So, if you see that FCC, BCC crystal structure, they have the kind of columnar dendritic structure actually grow in the 100 direction. So, Miller index of this 100 direction. So, that actually observed in case of FCC and BCC material. Now, if you see here that if you use the filler material, then weld metal composition changes, and that actually leads to the different type of the crystal structure for the weld and the base metal. So, that adding the filler material does not promote the epitaxial growth, and then new grains and nucleates basically forms at the fusion boundary when there is a addition of the other alloying elements, or maybe you can say that with the addition of the filler material during the welding process. So, during solidification the grains tends to grow perpendicular to the weld pool boundary, but the reason for that, there is a maximum temperature gradient actually exists along this direction, and then sometimes the columnar dendrites or cellular cells or cellular structure within each grain also grow in the within grain that try to grow in the easy growth direction. So, that means the different type of crystal structure material having the easy growth direction. For example, the FCC structure, the 100 is the easy growth direction, and we can observe specifically for the aluminum alloy and austenitic stainless steel, they are having this direction. BCC material also having the easy growth direction is 100, that is why if you look into the one unit cell, the 100 is basically along the one of the edge, along the edges. So, the carbon steel, ferrite, stainless steel, this type of materials also having the easy growth direction for the BCC material as the along the edge of the unit cell, that means 100 direction. Then in case of hexagonal close pack also having the easy growth direction, and that hexagonal close pack structure titanium and I think magnesium, and body center tetragonal structure tin also having the easy growth direction is 110, that means along the phase diagonal of an unit cell. So, different type of materials may have the different easy growth direction, and typically the epitaxial growth nucleation, not only growth, maybe first nucleation starts and then growth process starts. So, that epitaxial growth mainly happens probably the pure metal and during the welding process, and that along the normal to the phase boundary, because the driving force, the epitaxial growth in specific direction, probably the maximum temperature gradient along that direction. But the conclusion from here is that if we add the filler material, then the epitaxial growth may not be possible in that case. Now, what are the effects of the welding parameters on the grain structure? And just if we try to look into that is that if you look into the actual welded structure, what type of microstructure we can expect during the welding process at very high speed probably and at very low speed. So, if we see that high welding speed, the typical nature of the weld pool forms, that is the elongated weld pool. Sometimes teardrops can also form. So, if you look into the first figure, that it is a high speed, that if it is a elongated weld pool looks like, and when the heat source is moved one specific direction during the welding process. So, here the growth or grain actually grow with respect to that weld central line and almost perpendicular to the weld central line, but if it is very high speed, then it becomes axial, exactly perpendicular to the weld central line. And if we gradually reduce the welding speed, that means if very low speed, it takes the curvature and with respect to the weld central line. So, and from that weld central lines make a curvature and goes towards the outer periphery of the weld pool. So, these are the typical grain structure generally observed during the welding process. Now, if in case of low welding speed, the welding pool looks like the elliptical form, and trailing pool of the boundary of the teardrop shape, that means it is a very high welding speed. The weld pool is almost very nearly straight, and the growth also happens perpendicular to that. But columnar grains forms during these things almost the straight normal to the pool boundary. But in case of low speed, since the trailing boundary is of elliptical shape, then weld pool is basically make a curvature or make a curve, and the columnar grains are also curved in order to grow perpendicular to the weld pool boundary. So, making the initial curve, so that and finally, it makes the final curvature it's like that, almost perpendicular to the weld line. So, these are the typical weld grain structure that actually observed during the welding process. Now, we look into that weld metal nucleation mechanism. So, there is a nucleation mechanism, basically the mechanism of nucleation actually controls the microstructure of the weld pool. So, we need some understanding on the nucleation mechanism actually prevents during the welding process. So, two things are there. If you see actual welding process, that first is the growth of the columnar grains is basically interrupted by the formation of the new grains. So, new grains, formation of the new grains, they interrupt the growth of the columnar grain, and we see the growth of the columnar grain is actually the rear observed normally in the rear side of the weld pool. In the other way, when the new grains form, and that actually disturbs the growth of the epitaxial grains is interrupted. So, that disturbs the growth of the epitaxial growth of the grains also with the formation of the new grain. So, these two phenomena is counteracting with respect to each other. Then new grains normally are often equiaxed rather than the columnar kind of the structure. So, new grain forms here during the welding process, most of the we can find out it is almost the equiaxed structure rather than the columnar kind of the structure. Now, if you see the dendrites if you see the dendrite, the mushy zone behind the trailing portion, that means rear part of the weld pool, and in this case the mechanism of nucleation is basically depends on the several phenomena. One thing is the dendritic fragmentation. So, here if you see that dendritic fragmentation is happens because on the trailing side, the rear side of the weld pool, there is a formation of the dendrites, and due to the convective flow of the liquid metal within the weld pool, that actually brings the two mechanism, that means fragmentation of the dendrite. At the same times, the partially metals can be detached from the grains. So, these two promotes the formation of the heterogeneous nucleation most of the cases at the trailing side of the weld pool. So, the mechanism of nucleation during the welding process is better explained. One point is that dendritic fragmentation, then grain detachment, and that actually mainly promote the heterogeneous nucleation process. So, this figure also if we see that dendritic fragmentation grain detachment is very obvious. So, and that is that travel from one point to another point is due to the only the convection of the molten metal. And here also other way that sometimes the nucleation mechanisms is basically driven by the external gas, that on the surface nucleation is mainly promoted using some kind of the cooling gas. So, cooling gas also having effect on the nucleation formation during the welding process. So, if we look into details that dendritic fragmentation in the welding process, that whirlpool, and if we, it is obvious that whirlpool convection is the main reason, principal reason to cause the fragmentation of the dendritic tips in the specifically in the mossy zone. And then dendritic fragments are carried out by the bulk whirlpool and act as a nuclei for the new grain. So, that dendritic fragments is basically acts as a site for the nucleation, and then since it acts as a site for the nucleation. So, basically in this case we can expect the heterogeneous nucleation, and due to this continuously convective flow of the material, that always try to promote the heterogeneous nucleation, and the finally it is a kind of equi-X structure. So, that is why this dendritic fragmentation mechanism is also known as the grain refining mechanism of the weld metals. So, another mechanism is that in weld microstructure we can observe, that is a grain detachment. Here you can see that again the whirlpool convection cause the partially melted grains to detach from the solid liquid interface, and again they can act as a nuclei for the formation of the new grain. So, if you look into the figure, that heterogeneous nucleation here starts, and the mechanism for the equi-X dendritic structure, the mossy zone, and from there that promote the heterogeneous nucleation process and with respect to the welding direction. So, finally, the heterogeneous nucleation process, if the liquid metal contain mainly the heterogeneous nucleation process can be explained in that way, that if the liquid metal contains some foreign particles in the whirlpool, then that actually acts as a site for the nucleation. So, in this case the very energy barrier, the critical energy barrier for the nucleation process is basically less, because some external particles actually start the initiates the nucleation process. So, that is why we also observe from the solidification theory also that in homogeneous nucleus and heterogeneous nucleation, theoretically almost the size of the critical radius of the nucleus are the same, but the energy barrier. So, amount of energy required to form the homogeneous nucleation is more as compared to the heterogeneous nucleation, because heterogeneous nucleation the external particles actually promotes or the site of the nucleation. So, barrier requirement is less in this case, energy barrier requirement is less. Now, if you look into that, what are the welding parameters that actually affect on the heterogeneous nucleation process. So, first thing is that formation of the equi-X grains is enhanced by the higher heat input and the welding foot. So, it is observed from the directly the equi-X grains from the microstructure, observe that higher heat input and very high welding speed, that actually promotes the equi-X structure. But with the increase in heat input as well as with increasing the welding speed, the temperature gradient at the end of the whirlpool is actually reduces. So, although there is a heat input is very high, but at the same time the welding speed is also high, that promotes or that actually reduces the temperature gradient in the whirlpool. Other way, with increasing the very high welding speed and at the same time thus increasing the welding speed also the increases the rate of the solidification. So, increment of this one is the by decrement of the G value, that means by decrement of the temperature gradient, and at the same time increment of the solidification rate, actually that actually promotes lower down of the G by R ratio. So, G by R ratio should be decreased. So, in that sense that G by that actually effect of the G by R ratio. So, we can link with the type of the nucleation mechanism with respect to the welding parameters. Welding parameters means here the heat input and the welding speed. These are the two parameters. So, ratio of the GR again can be linked with that constitutional supercooling. That means, if ratio of G by R should be decreased, that means G by R ratio decrease, and that actually promotes the constitutional supercooling in front of the solid liquid interface. So, therefore, should be increased G by R ratio should be increased for the equi-axed grain formation. That means, G by R should, if we high value of the G by R ratio, that actually promotes the equi-axed grain formation. Here you can see the, so G by R ratio, from here you can see the G by R ratio is very high, then it actually promotes the planar kind of the solid interface, or if G by R ratio is low, that means low value of G by R ratio actually promotes the equi-axed structure. So, in this case, the if we want to find out the low value of the G by R ratio, that means in that case the it promotes the equi-axed grain structure. Now, how to control on the grain structure? So, we some overall knowledge about the oil microstructure that actually significantly affect the mechanical properties. So, what way it affects the mechanical properties is that normally the oil metal tensile strength increases if the amount of the equi-axed grain is more. That means, within the solidified zone, if the amount of the equi-axed grain is more, that actually that finally affects the increment of the oil joint strength. If equi-axed grains also, that means presence of the equi-axed grains in too much in the welded structure, that actually reduces the susceptibility of the weld metal for the solidification cracking during the welding process. Also, there is another advantage, that if fine grain, that means overall grain size is very fine, that actually improves the ductility and toughness properties of the weld joint, specifically the steels, and specifically the in case of the steels and stainless steels welded cases. So, it is always advantageous to produce the equi-axed kind of or fine microstructure in the welded joint, that always try to improve the mechanical properties of the weld joint. But therefore, to find out the very fine weld microstructure, then what may be the factors or what way that actually impact on the microstructure during the welding process. So, first thing is the inoculation. Inoculation is that as the inoculating, if we add the inoculating agent that promote the kind of heterogeneous nucleation process. So, if there is a promotion of the heterogeneous nucleation, then it is tried to form the almost kind of equi-axed kind of structure. So, this is one way to promote the equi-axed structure in the oil joint. Next is the oil pool steering action, and that means if it is possible to mechanically steering the oil pool, then it is possible to more or less kind of equi-axed kind of structure is possible to produce. Then arc oscillation. So, not keeping the arc as a fixed position, rather if you try to oscillate the arc, that also try to promote the formation of the equi-axed kind of structure. Arc pulsation, instead of using the continuous arc, if we use a pulse arc, then it also promotes the equi-axed kind of structure. Of course, sometimes the simulated surface nucleation, if we use some extra heating or extra cooling system using the shielding gas on the surface of the liquid molten pool, that also try to promote the formation of the equi-axed structure. So, these are the different methodologies or techniques, that way we we can produce the Week-6 structure in a solidified weld zone, and that is advantageous in terms of the we can expect the very good weld joint properties. Now, come to that next other topic, that is the phase transformation. So, we will try to look into some overall idea of the phase transformation, and it is very specific to the welding process and very specific to few materials. So, we have some idea about the phase transformation, that means there are 3 different way we represent the different diagram the phase transformation in case of metallic materials. So, first is the equilibrium phase diagram. Normally, we try to represent the binary alloy system. So, 2 alloy, assume that the material is the consists of the 2 alloy, and we can draw the equilibrium phase diagram for this alloy. So, equilibrium phase diagram is basically drawn at the almost theoretically the rate of the cooling is almost 0. That means, we try to follow the equilibrium condition of the phase transformation. So, that means there is almost no effect of the time here, that means we can neglect the effect of the time in this case. But if you look into the other diagram, the time temperature transformation diagram, we represent the different phase transformation line with respect to the axis, as a one is the temperature axis, another is the time axis. Similarly, in case of the continuous cooling transformation, that means that is called the CCT diagram. Here also we can plot that the transformation diagram following the constant cooling rate of the constant cooling rate, and here one axis represents the y axis normally represents the temperature, and x axis represents the time here. So, these are the 3 different diagram we normally use to explain the phase transformation, and in case of the mostly alloy element, and we are assuming all these cases we are assuming that it is a binary alloy system. But the equilibrium phase diagram is mainly to know the what is the phase presence there, but time temperature diagram is the transformation of the phase at constant temperature, which is most of the cases not practical, because and practically the transformation happens not as a constant temperature, rather there is a variable temperature. That means, the variable temperature can be better represented as a in terms of the cooling rate, constant cooling rate. So, that to represent the transformation using the constant cooling rate, that is better represented in the diagram of the CCT diagram. So, most of the heat treatments actually follows the CCT diagram to find out what is the final microstructure, depending upon the what is the cooling rate is followed during the process. It may be solidification process or it may be welding process. So, now if you look into the welding process, it is actually subjected to the any like other practical process subjected to the variable cooling rate, also variable temperature. So, but till we can use the phase transformation diagram, a CCT diagram or TTT diagram to explain the transformation of the different one phase to another phase with respect to time, with respect to temperature, with respect to the different fixed cooling rate. Now, melt zone, that means oil pool molten zone is basically subjected to the solidification, but heat affected zone solidification means here the transforms from the solid liquid phase to solid phase, but heat affected zone it is in solid state, but maybe solid state, but one phase to another phase transformation may happen. That means, it is a solid state phase transformation happens in the heat affected zone. So, this the typical overlook of the phase transformation we observe in case of the welding process. Now, we have tried to represent the phase diagram, because this phase diagram is helpful the composition of the different phases exist within the microstructure. So, here I just try to represent the iron carbon equilibrium phase diagram. Here you can see that y axis represents the temperature, that means at different temperature what is the different phase presence, and the x axis represents the weight percentage of the carbon. That means, it is a binary alloy system. Here The one component is the iron Fe and another component is the carbon. So, when Fe and carbon are mixing up to certain position and depending upon the temperature, different phase presents. For example, the phase boundary is represented here also. So, that gamma it represents by the austenitic, this is the austenitic phase. So, that means with this iron along with the different percentage of the carbon, the constitutes austenitic phase at the different range of the temperature. So, then another phase is the alpha ferrite. So, it is only ferrite or sometimes it is called the alpha ferrite. So, alpha ferrite, here you can see the alpha ferrite phase exists, it is a very low the percentage of the carbon. Basically, that carbon is the here the maximum solubility limit of the carbon within this phase produces is I think around 0.02 percentage of the carbon. So, that constitute the one phase, depending upon the that phase having the secondary second alloy, that means here is the carbon up to certain percentage and they constitute one single phase alpha phase. So, that is the alpha phase and this alpha phase is having the some maximum amount of the solubility of the second phase, that means carbon here. Next, the other phase, the similarly austenite is the single phase structure, that means single phase structure, but it is having the maximum solubility of the certain carbon percentage exist in austenitic structure also. Now, if you look into the other within this phase boundary and this phase mixture exists alpha plus gamma, that means ferrite, it is a this zone represents the mixture of the ferrite and austenite, and here is the beta phase is basically cementite. So, this is a one phase, the maximum solubility of the carbon in the cementite phase is the 6.67 percentage of the carbon and they constitute one single phase, that is called the cementite. So, this phase here at this position, the here the mixture of the two phase exist, the beta phase and the gamma phase, that means austenitic plus cementite phase mixture, and here you can see this zone two different phase, the ferrite and the cementite fixtures, but there is no existence of the austenitic phase this at this zone. That means that zone means it is defined over the certain temperature range. So, if we know for a specific binary alloy system, this phase diagram we will be able to find out from this phase diagram that coexistence of the single phase or mixture of the two different phases over the temperature range, we will get all kind of information from this phase diagram. But here this phase diagram is can be utilized if you see that with this phase diagram is no longer, it is equilibrium phase diagram, it is no longer related to the time component. So, therefore, rate of the cooling, all these things is having no importance here. Here we can constitute the if one phase mixture, if we know that one phase mixture, we can using the Leber rule we can find out what is the proportionate way the different phases exist within the mixture of the phases. So, that kind of information can be well extracted from the phase diagram. Anyway, if we look into that in the welded structure, so information of the welded structure, what are the different phase transformation may happen or how it can be predicted in the final structure with respect to the type of the material or composition of the material. For example, first if we look into that stainless steel SS310, normally the nickel content is high in this type of the stainless steel. So, this final microstructure consists of the different phases like that primary austenite dendrites and interdendritic delta ferrite between the primary and secondary dendritic arm. So, delta ferrite structure is also there and the austenitic phase and the ferrite phase also there, but the delta ferrite mainly exists in the primary and secondary dendritic arms. In that spaces we can find out the delta ferrite. So, this consists of the two different phases, the delta ferrite and the austenitic phases, but they coexisted and making a homogeneous structure. Next, if we look into the material stainless steel, that high chromium SS309, that is chromium content is very high in this case as compared to the nickel content. So, these microstructures consist of the primary lath type delta ferrite in an austenitic matrix. So, that means overall structure is the austenitic matrix. So, within the austenitic matrix the delta ferrite exists in a type of lath. A lath type delta ferrite exists within the structure. So, their microstructure is maybe different from the SS310, although both the cases the phases, austenitic phases as well as delta ferrite phases exist, but the distribution of the delta ferrite, the shape and size may be different in these two cases. So, normally the solid redistribution during the solidification is basically reduced and in presence of the high cooling rate, because at very high cooling rate probably the transformation of the one phase to another phase chances are, or transformation time is very less, probably that may be the reason for that redistribution. During the redistribution of the different solid constitute or solid phases within the structure is basically reduced at very high cooling rate. And for this type of material specifically high cooling rate, at the same time for the low chromium and nickel ratio. When the chromium and nickel ratio is very low, in this case the redistribution of the solid phases can be reduced at high cooling rate. But if the chromium and the nickel ratio is very high, so in this case the delta ferrite is as the primary phase and the secondary, and their ferrite content actually increases with increasing the cooling rate. So, delta ferrite, if the chromium and nickel ratio is very high, in this case the delta is the primary phase is the delta ferrite, and the ferrite content is basically increases with increasing the cooling rate, because the transformation from delta ferrite to the austenitic transformation having the less time to occur is basically high cooling rate. So, if we see that normal, if we look into that, like this type different type of the material, their different phase exist within the microstructure, but the phase, that formation of the primary phase, secondary phase, it depends on the ratio of the other alloying elements. So, just this is one example, that if nickel and chromium is the main constituent for the stainless steel, if their ratio are different in these two cases, we can expect the different kind of the microstructure. So, of course, in this case we need to the in depth study of the different type of the microstructure for other material. Here we try to like another example for the weld microstructure in case of the low carbon steel. If you see that in low carbon steel, that austenitic phase is cooled down from the high temperature, and it called the alpha ferrite basically nucleates specifically at the grain boundary and specifically from the Wilkinson pattern. So, specific pattern actually it forms when austenitic cool down to the from the high temperature to the low phase ferrite phase. So, at low temperature it is too slow for the Wilkinson ferrite structure to grow to the grain interior. So, in that case acicular ferrite nucleates from the inoculations. So, this low carbon steel is basically forms the different type of the structure that actually that is called the grain boundary ferrite structure, polygonal ferrite structure, Wilkinson pattern ferrite structure, acicular ferrite, upper bainite, lower bainite. So, this type of the different kind of the structure can be produced by the weld microstructure, or we observe in the weld microstructure of the low carbon steel. Similarly, if you look into the C60 diagram, continuous cooling diagram for the 434 type of steel, we can find out that at the different range of the cooling rate, if we follow, we can find out the different structure. So, it is a very high cooling rate, probably we can get the martensitic structure. Further less of the cooling rate, bainite structure, very low cooling rate, gradually we can ferrite and perlite or some mixture of the ferrite and perlite. So, all this kind of structure we can expect in low carbon steel, but this the CCT diagram in this case is used to define that if we follow the different cooling rate, then we can expect the different kind of the structure. Of course, this structure maybe changes the if the composition changes in even in case of the low carbon steel, or maybe alloying elements change low carbon steel, then probably we can get the other kind of the structure, or there the one phase is distributed in different shapes within the other phase, that all can produce the different type of the microstructures. So, all can be depend or explained in terms of the rate of the different cooling rate. So, that is why it is very important to estimate during the welding process, or it is most of the cases we can find out the rate, the link between the rate of the cooling and the typical microstructure, and finally, that microstructure can decide the what is the mechanical properties of the weld joint, but the link between all these three components is not very straightforward or may not be linear always. So, it is always exists the non-linear relationship. So, that relationship is varies depending if there is a change of the alloying elements. Now, next topic we will try to look into that solidification cracking, that is more related to the in the welding process. We see that cracks normally occurs during the welding of the regions. That first is that during the solidification process the crack occurs maybe due to the temperature gradient. So, if there is the existence of the temperature gradient, that also brings the thermal strain. And next possible reason for that is the compatibility of the different phases due to variation their compositions, and third, embrittlement of the grain boundary. So, sometimes the if grain boundary becomes embrittled, that actually induce the kind of the solidification thing, and another reason for the volumetric contract during the cooling process. So, different phase having different constitutes. So, it is not necessary that during the cooling process there may be the contraction of the within the there is a change microstructure due to the changes in the microstructure, there may be the contraction in the volume, that actually may induce some amount of the cracking phenomena during the solidification process.